In the previous class, we discussed about some basics of transmission line, and we have seen that a short section of transmission line can be represented in terms of its lumped equivalent circuit. In this lecture, we will cover the following: the telegrapher's equation, the wave propagation on a transmission line, then we will cover the lossless transmission line, and then terminated lossless transmission line, and finally, special cases of terminated lossless lines. So, we start with telegrapher's equations, how we develop these equations. We have seen that the lumped element circuit model of a short section of transmission line can be represented by the equivalent circuit as shown here. If we apply Kirchhoff's voltage law and current law on this circuit, then we get a set of equations relating the current and voltage on the line. So, this is the equation where voltage is related to the current and the resistance, inductance, capacitance and conductance of the equivalent circuit model. Similarly, we can, if we apply KCL here, we can get another equation. Please note that both the equation we get after the application of KVL and KCL, these equations represents voltage and currents which are both function of distance z and time t. If we rearrange the previous equations, we get and similarly for the current equation, these two sets of equation now can be divided on both sides by delta z, and as delta z tends to 0, we get the following sets of equation. Now, these equations are known as telegrapher's equation. It may be noted that the spatial derivative of the voltage in the first equation is related to the time derivative of current. Similarly, the space derivative of the current in the second equation is related to the time derivative of voltage. So, this in one way these equations they are coupled, and we have both voltage and current present in this equation. Now, let us see how we can infer wave propagation on a transmission line. The voltage V and I, which are function of distance z and time t, can be expressed in terms of phasors. The instantaneous line voltage and current can be expressed as V z t is equal to real part of a voltage phasor which is a function of position z multiplied by e to the power j omega t. Similarly, I z t is the real part of a current phasor I z multiplied by e to the power j omega t. Now, the voltage and current on the transmission line can be expressed exclusively in the form of phasors, and we note that the partial derivative del t of e to the power j omega t will contribute this term j omega. So, from these two equations we get the following phasor equations: dV dz is equal to minus r plus j omega L I of Iz, and d Iz dz is equal to minus g plus j omega c Vz. Now, if we notice here, the space derivative of the voltage is related to current phasor. Similarly, the spatial derivative of the current phasor is related to the voltage phasor. Now, we can decouple these two equations to form the wave equation for the voltage and current. So, if you take derivative on both sides of this equation and substitute d I dz from here, then we can write d square Vz dz square is gamma square Vz. So, in this equation we find that it is only the voltage phasor V is involved. And rearranging the term, we can write of this form: d square V dz square minus gamma square V equal to 0, where gamma, which is equal to r plus j omega L into g plus j omega c whole under root, is the complex propagation constant and can be written as alpha plus j beta. We can also in the same manner form the wave equation for the current. Now, solution to these wave equations are of the form: V as a function of z is V naught plus e to the power minus gamma z plus V naught minus e to the power gamma z. Similarly, I a function of z is I naught plus e to the power minus gamma z plus I naught minus e to the power gamma z. Here we find that e to the power minus gamma z and e to the power plus gamma z represent wave propagation in positive z and negative z direction respectively. We can also find an alternative form of Iz, which is found as follows: we have dV dz is equal to minus r plus j omega L Iz. If we substitute the equation for Vz and rearrange the terms, then we get Iz is equal to gamma by r plus j omega L into V naught plus e to the power minus gamma z minus V naught minus e to the power gamma z. And this can be written as Iz is equal to 1 by z naught V naught plus e to the power minus gamma z minus V naught minus e to the power gamma z, where z naught we are defining as r plus j omega L divided by gamma. If we compare this expression for Iz with the earlier expression we derived, that means Iz is equal to I naught plus e to the power minus gamma z plus I naught minus e to the power gamma z, then this characteristic impedance z naught of the transmission line can be defined as V naught plus by I naught plus is equal to z naught is equal to V naught minus divided by I naught minus. Now, in terms of the parameters of the transmission line, Z naught is equal to r plus j omega L divided by gamma, which is equal to r plus j omega L divided by g plus j omega c, if we substitute the expression for gamma. It may be noted that Z naught is a function of the operating angular frequency omega. If we come back to the time domain form, then we can write V as a function of Z and t as real part of voltage phasor Vz e to the power j omega t. And substituting expression for Vz, writing gamma equal to alpha plus j beta, we get this equation. And then expressing V naught plus and V naught minus in their magnitude and phase form, we get this form of representation of V z t. Retaining only the real part of this equation, we can write the voltage on the transmission line as a function of Z and t given by V naught plus magnitude cos omega t minus beta z plus phi naught plus e to the power minus alpha z plus V naught plus mod cos omega t plus beta z plus phi minus e to the power alpha z. Phi plus and phi minus is the phase angle of the complex voltage V naught plus and V naught minus. The first term represents a wave which is travelling in the plus z direction. Similarly, the second equation represents a wave travelling in the minus z direction. We consider a simple case where we assume that alpha is equal to 0, that means the wave does not attenuate as it propagate. Further, V naught plus phase angle phi plus is 0. So, with this assumption, let us now plot this first equation. We can see that t equal to 0, this equation as a function of z can be plotted as shown, and let us follow the movement one particular point on this wave which is marked here. So, at t equal to t by 4, we find that the point moves towards the plus z direction. Similarly, at t equal to t by capital T by 2, that means half the time period, the point has moved further and it continues. So, this equation essentially represents a wave which is travelling in the plus z direction, and here in this case we have considered the wave does not attenuate. The phase velocity of the wave is given by omega by beta, and this is equal to lambda wavelength of the wave into frequency f, and also the wavelength on the line is given by 2 pi by beta, which we see from this relation. Now, we consider a special case of a lossless line. For a lossless transmission line, we will have r equal to 0, g equal to 0, and if we put these values, then In the expression for the propagation constant, we get gamma becomes j omega root L c. Therefore, alpha, the attenuation constant becomes 0, and beta, the phase constant, becomes omega root L c. The characteristic impedance, wavelength and phase velocity of the lossless line can be expressed as Z naught becomes root L by C, and now it is not a function of omega. Lambda is 2 pi by beta, which can be written as 2 pi by omega root L c, and phase velocity V p, which is omega by beta, becomes pi by root L c. Now, for a lossless transmission line, when alpha is equal to 0, the voltage and current phasors can be written as shown in these two equations. We consider a particular case of a terminated lossless transmission line. Here we see that the lossless transmission line having characteristic impedance Z naught and phase constant beta is terminated to a load impedance ZL. VL represents the voltage across the load and IL is the current flowing through the load. Please note that the reference distance Z is equal to 0 is considered to be at load location, and then the distances are calculated from the load towards the source which excites the line. Now, this particular problem illustrates a fundamental property of distributed system, the wave reflection in the transmission line. So, we assume the voltage at Z less than 0 is incident from a source, and it sets up a waveform V naught plus e to the power minus j beta z propagating in the plus z direction. So, this voltage when moves on this line finally reaches the load, and it sees a difference in the impedance, and this results into a reflected wave which travels back towards the source. So, we have seen that the voltage on a transmission line and the current can be written in the forms as shown. Now, if you consider at z is equal to 0, then the load impedance ZL becomes V naught by I naught, and substituting z is equal to 0 in the expression for the voltage and current, we get V naught plus V naught minus divided by V naught plus minus V naught minus into Z naught. And from this equation, if we solve for V naught minus, then we get V naught minus is ZL minus Z naught divided by ZL plus Z naught into V naught plus. Thus, the voltage reflection coefficient we define as V naught minus divided by V naught plus. This is the reflected voltage at the load, and this is the incident voltage at the load, and their ratio of the reflected to voltage to incident voltage is the reflection coefficient, and we can find this gamma reflection coefficient to be ZL minus Z naught divided by ZL plus Z naught. So, given the load and the characteristic impedance, we can find out the reflection coefficient at the load. Now, once we introduce this reflection coefficient gamma, we can rewrite the expression for the voltage and current, where V naught minus is replaced by V naught plus into gamma and V naught plus is taken out. So, we have the expression for the voltage and current as shown. Now, we can see that the voltage and current on the line is a superposition of incident and reflected wave, and when both incident and reflected wave are present on the line, it gives rise to standing wave. Please note that the reflected wave will become, it will vanish for gamma equal to 0, and the condition to achieve this is ZL is equal to Z0, then gamma will become ZL minus Z0 divided by ZL plus Z0 equal to 0, and this particular condition, when the load impedance is same as that of the characteristic impedance of the line, this condition is called the matched condition. The average power flow along the line at any distance z is given by P average is equal to half of real part of Vz into Iz conjugate. And once we substitute the expression for the voltage and current phases in terms of the forward and the incident and the reflected waves, we can write this equation. And then we can further simplify it and get a form which is shown here. Please note that in this expression, the two middle terms, when combined, they give rise to an imaginary term, and this term can be dropped, and retaining only the real part, we get average power to be equal to half of V naught plus magnitude square divided by Z naught into 1 minus mod of gamma squares. Return loss is the power lost due to the load mismatch, and it is given by RL equal to minus 20 log 10 mod gamma dV. For a matched load, gamma is equal to 0 and RL is infinity, there is no reflected power. Similarly, when gamma is equal to 1, that means the entire power is reflected, return loss is 0 dB. For a passive network, the return loss is a non-negative number. For a mismatched load, we can write Vz is equal to V naught plus into e to the power minus j beta z plus gamma e to the power j beta z, and if we take the magnitude of voltage, then we can write magnitude of Vz is equal to V naught plus magnitude into magnitude of 1 plus gamma e to the power j 2 beta z. Now, if you consider at a distance z is equal to minus L, then we can substitute this z by minus L and we get this expression. And finally, when gamma is replaced by its magnitude and phase term, we get magnitude of V at a distance z is equal to minus L to be V naught plus magnitude into magnitude of 1 plus mod gamma e to the power j theta minus 2 beta L, where theta is the phase angle of the reflection coefficient. we can see that from the previous equation, the voltage magnitude, it will vary with z, and the voltage magnitude oscillates with position along the line, and from this equation V z minus L magnitude is equal to V naught plus magnitude into 1 plus mod gamma e to the power j theta minus 2 beta L. We find that when the phase term becomes 0, in that case we get the maximum value of the voltage and we denote it by V max, and V max is V naught plus magnitude into 1 plus mod gamma. Similarly, when this term it becomes pi, this phase term will become minus 1 and we will get V min is equal to V naught plus into 1 minus mod gamma. So, the voltage depending upon the position on the line will keep changing between V max and V min. Please note that the magnitude of the reflection coefficient becomes 1 when the load is a short circuit or it is an open circuit. For both these cases, the reflection coefficient magnitude will become 1, but the difference is that when it is a short circuit, a voltage minima will be 0 because magnitude of reflection coefficient is 1 and it will be formed on the load location. Whereas, for a open circuited line, a voltage maxima will be formed on the load location. We introduce a term which is called voltage standing wave ratio, and this is a measure of the mismatch of the line, and we define VSWR is equal to V max by V min, which is given by 1 plus mod of gamma divided by 1 minus mod gamma. VSWR is a real number, it lies in the range 1 to infinity. VSWR is equal to 1 corresponds to perfect matching, there is no reflected wave, that means gamma is 0, and VSWR tending to infinity gives perfect mismatch, that means all the power is reflected. Please note that a line terminated to a short circuit or an open circuit represents such condition when VSWR becomes infinity, because in both the cases mod gamma will become 1 and VSWR will approach infinity. So, when we have voltage variation on the line between this V max and V min, the distance between the successive maxima or minima on the line is lambda by 2, while the distance between a maximum and a minimum on the line is lambda by 4. So, at a distance L is equal to minus z from the load, the input impedance towards the load is given by, if we substitute V with z is equal to minus L and then we take the ratio of voltage at z is equal to minus L and current at z is equal to minus L, then we get this expression. Now, we substitute the value of reflection coefficient gamma then we can write Z in this form, and when these terms are rearranged, we get the final form of the equation as Zin is equal to ZL plus J Z naught tan beta L divided by Z naught plus J Z L tan beta L multiplied by Z naught. So, this is a very important equation and it gives the input impedance that will be seen at a distance L from the load looking towards the load, and this is the transmission line impedance equation. Let us now consider some special cases of terminated lines. As shown here, we have ZL set to 0. This particular case is the case of short circuited transmission line, and in this case the reflection coefficient gamma will become -1. VSWR on the line is infinite. So, we can obtain the voltage and current on the line as, once we replace the reflection coefficient gamma is equal to -1, the voltage expression becomes like this. Similarly, the current expression becomes as shown in the figure. Now, if we consider at a distance minus z is equal to L, so we can write V z is equal to minus L to be equal to V naught plus e to the power j beta L minus e to the power minus j beta L, and this term can be rearranged, and finally we find that voltage as a function of distance L can be written as 2 j V naught plus sin beta L. Therefore, the voltage V divided by 2 z V naught plus is equal to sin beta. In the same manner, we can find out the expression for the current at a distance L from the load, and this current at a distance L from the load can be written as 2 V naught plus divided by Z naught cos beta L, and therefore, the input impedance seen at a distance L from the load can be written as Zin is equal to j Z0 tan beta L, and you can see that the same expression if you of the impedance you get if you divide the voltage expression at a distance of L from the load divided by the corresponding current expression. Now, this voltage, current and input impedance variation is plotted along the line for different distances from the load. So, we find that the voltage variation gives a sin beta L variation, and therefore, you can see that a voltage minima, since it is a short circuited line, occurs at the location of ZL, and then voltage reaches its maxima, and then at a distance of lambda by 2 it becomes minimum again. Whereas, if you look at the current expression, the current on the line at a distance L from the load varies as cos beta L. So, the short circuit point, that means at the load location we have the maximum current, and then it decreases to its minimum value at a distance of lambda by 4 from the load, and it can be seen that when the voltage is maximum, the current at its minimum. The impedance variation is given by of the form of 10 beta L, and if we write input impedance is purely imaginary, and if we write x in by z naught, then we see that the variation, it is initially inductive till the length is lambda by 4, then it becomes capacitive, then it becomes inductive again. So, this is how a short circuit terminated line will behave in terms of voltage, current and impedance variation. Let us discuss another case of terminated line. In that case, we consider ZL to be infinity. That means, it is the case when the transmission line is terminated to an open circuit. And in this case, we can write the reflection coefficient at the load gamma to be equal to 1 minus Z naught by ZL divided by 1 plus Z naught by ZL, and when ZL tends to infinity, in the limiting case the gamma will become 1. Once again the VSWR will become infinity. The voltage and current on the line now we can obtain as here we can see that the gamma has been replaced by plus 1 here. And rewriting these expressions for a distance L from the load, we can find that V at a distance of L from the load is 2 V naught plus cos beta L, and similarly if we find out the current, at a distance L from the load can be found to be 2 j V naught plus divided by Z naught sin beta L, and the input impedance once again if you calculate V by I at a distance L from the load, Z in becomes minus j Z naught cot beta L. As before, we plot the voltage, current and impedance variation along the line when the line is terminated to an open circuit, and we find that in this case the voltage variation is given by cos beta L and a voltage maxima occur at the load location, whereas a current minimum occurs at the load location, because no current flows through the open circuit, and the impedance becomes purely imaginary, and x in by Z naught, as we can see for line length less than lambda by 4, it is negative. So, it is capacitive and then it becomes inductive from lambda by 4 to lambda by 2, and this varies periodically over the length of the line. Let us now come to another special case where we consider a junction of two transmission lines with different characteristic impedances. So, we can see that the line shown in blue has a characteristic impedance Z naught, and it is connected to another line having a characteristic impedance Z 1. So, the reflection coefficient at the junction, if we compute looking from this line, it will be given by Z1 minus Z0 divided by Z1 plus Z0, and the voltage wave on the line now can be written as. So, we will have the incident voltage V naught plus e to the power minus j beta z and the reflected voltage V naught plus into gamma e to the power j beta z, which is travelling in the minus z direction, and both these waves will exist in this part of the line for z less than 0. When it comes to the wave propagation in the other part of the line, we find that the part of the voltage that is transmitted to the second line, that means for z greater than 0, can be written as V z is equal to V naught plus e to the power minus j beta z into a transmission coefficient T. And if we consider the fact that the voltages at the two sides of this junction has to be same, that means at z is equal to 0, then we will get 1 plus gamma will be equal to T, and if we substitute the expression for gamma, in that case we get T is equal to 2 Z1 divided by Z1 plus Z0. Now, it is also termed as insertion loss, and it is given by insertion loss is equal to minus 20 log 10 mod of T dB. We continue with the junction of two transmission line with different characteristic impedances, and we see that if we have a transmission line of length L is equal to lambda by 2, then Zin becomes equal to ZL. We have seen that the input impedance of a lossless line terminated to an impedance ZL is given by ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L, and whole thing multiplied by Z0. Now, depending upon the location where the input impedance is observed, we find that if L is equal to lambda by 2, then Zin becomes equal to ZL, and a half wavelength line or any multiple of lambda by 2 does not transform the load impedance regardless of the characteristic impedance of the line. So, this is a property that if we take a transmission line of length lambda by 2, the or multiples of lambda by 2, in that case the input impedance seen is same as the load impedance. We consider another case when the transmission line is an odd multiple of lambda by 4 in length. So, in this case we get, using this equation, Zin becomes equal to Z0 square divided by ZL. So, for a transmission line, this type of transmission lines sections which are of quarter wave length are known as quarter wave transmission line and can transform the load impedance to another and can transfer the load impedance in an inverse manner depending upon the characteristic impedance value. The properties of quarter wave transformer we will study in detail later. So, we have discussed the various issues related to the wave propagation in a lossless transmission line. We have seen the special cases when the lossless line is terminated to a short circuit or an open circuit. Similarly, we have seen the impedance transformation property of half wave transmission line, quarter wave transmission line. In the next lecture, we will see transmission line having loss. In fact, we will cover the lossy transmission line, particularly when the loss is small. Then we will consider another special case which is called a distortionless line, and finally, we will conclude our discussion in that lecture by considering the terminated lossy lines.